So welcome everybody to this latest A2 video on 162 Maths. In this video we'll be going through statistics with a focus on binomial distribution with normal approximations. Now we'll be introducing this topic as well as going through some very common examples that you'll get both in textbooks and generally in exams. However, I will do another video where we focus purely on exam style questions. Now when n and p are such that np is greater than 5 and nq is greater than 5, where q is obviously the probability of not a success, or 1 minus p, then x can be assumed to be binomially distributed with a sample size of n and a probability of success p can be approximated by a normal distribution with the same mean and variance, where x is assumed to be normally distributed with a mean of np and a variance of npq approximately. Now, the larger the value of n and the closer that p is to 0.5, the better the approximation. And that's a really important statement that I would definitely highlight in your notes. If a question, and it's usually part C of a question where a question asks you to give a reason as to why this is a good approximation or why this is not a good approximation, is to look at the sample size and to see how close the probability is to 0.5. Now the normal distribution is continuous data, whereas a binomial is using discrete data, so a continuity correction must be used. Now you might be asking what is meant by a continuity correction, which is why we're now going to talk about it. So as mentioned, the normal distribution uses continuous data, whereas binomial distribution uses discrete data. So when you are converting a binomial question to a normal approximation, we need to adjust the parameters. So in a binomial distribution, we have our parameters set as knowing what the sample size is and what the probability of a success is. Now to convert that, obviously when we're using normal distribution, we need to know what the mean and the variance is. So what we then need to use to find those two bits of information is use this. Now if I just label this as binomial and this as normal, then that should make a little bit of sense. Now in terms of your normal typical binomial distribution questions, that obviously you can get a big waffle of a paragraph of a story, a situation that you then need to work out. But basically what you are doing is you're going to be finding one of these probabilities. Now what's really important is that you are able then to convert that into typically what a normal distribution question would look like, where you're looking at cumulative data rather than looking at those. Now with this, because obviously the data is continuous with normal distribution and discrete with binomial, is what you need to do is look at error bounds. So because the data is continuous, if you're wanting the probability that x equals 11, then if you're wanting that actual value to convert that into a normal, then what we need to look at is the lower bound, which is 10.5, and the upper bound, which is 11.5. And that will give us, so this would be a binomial question, and this would be the approximation for a normal. So you either need to go either plus or minus 0.5 on your actual values of x that you are finding. Now the diagram, as you can see here, kind of represents what it is that you're going to be looking for, but majority of it is general common sense. So you just need to know, are you including that value of a, or are you not, or you're not wanting that? And if you are wanting it, then you need to go 0.5 below, and if you're not wanting it, you need to either go 0.5 above or below, depending on the direction of your inequality. But this is definitely something that I would include in your notes when talking about the continuity correction. Now some questions worth 1 mark might ask you to state the continuity correction, and this is basically what they are asking. This here and this notation is your continuity correction. So if you get asked to work it out, then what they are wanting is this, what's in this box here. So to try and get some understanding of this, let's have a look at some examples. So let's have a look at this first question. Now this first question resembles something that you'd most likely find in a textbook rather than an exam paper, but kind of goes through the basics of understanding some of the vocabulary and some of the things that are asked in questions. So in terms of this first step, it says that the discrete random variable x can be assumed to be binomially distributed with a sample size of 60 and a probability of a success being 0.45. So this is my n value and this is my p value. Now this can be approximated by the continuous random variable y, which can be assumed to be normally distributed with a mean of 27. So this is my mu and this is my variance. Now remember that to work out mu in a normal distribution, that is n times p, and the variance is n times p times q. So in other words, where those two numbers have come from is mu has come from 60 times 0.45, and the variance has come from 60 times 0.45 times 0.55. So typically you may be asked to work out what this is, but in this question they've actually given those values, so again they've done a bit of work for you. Now in this question it says apply a continuity correction and to write down the equivalent probability statements for y, and then the second part then asks us to show that the two distributions yield roughly the same probability in each case. So let's have a look at what this means. I'm going to try and do these in different colours because obviously in terms of space we are relatively quite limited. So in terms of A, so all I want to do is convert this probability from binomial into a continuity correction. So because we're looking for x is equal to 23, then I want to be looking at values of 22.5 and 23.5. in terms of the continuity. Now this here, now again in terms of the equal sign, obviously in normal distribution we can't have an equal sign, so that's basically what we would get. Now if you were to include it, it's not really be a problem, it's just that with exact values it's always going to be 0. So again, if you forget to write that or you do write it, you shouldn't really be penalised for it, but I would say just go for without. So in terms of part 2, where we're actually working this out, so for binomial what we're looking for is our parameters are 60 and 0.45, and we are wanting to work out the probability that x equals 23. Now if you type this into your calculator, which you probably be expected to do, you should end up with an answer of 0.06 to 3 SF. Then if I look at the normal distribution, so for norm, and I'm working with the parameters of 27 and 14.85. So remember that for standard deviation, it's going to be the square root of 14.85. And what I'm wanting to work out is the continuity correction. So it's going to be 22.5 and 23.5. So for this, again, I'm going to use my calculator. I'm going to have the norm CD. Lower bound is going to be 22.5, the upper bound is going to be 23.5, the mean is going to be 27, and the standard deviation is going to be square root of 14.85, in which we get that this probability should equal 0.0604. Now as you can see, in terms of comparing the two, that this value here and this value here are very close. So very, very similar. And that'll be the part for part A. So moving on to part B, so let's just get rid of all of this. Should be right. So this time let's go for a different colour, so let's look at B. So for B, our continuity expression, because we're looking for values that are less than 50 or less or equal to 50, then I want to include 50. So for this, what I'm going to have is the probability that y is less or equal to 50.5, because I want to include 50, so I need to go right up to its upper limit, and that's what I should have. And again, I don't know why I keep putting this equal sign, but we're there, should have that. Then for 2, what we need to do is work out the actual probability. So again, for the binomial, we've got a parameter of 60 and 0.45, and what I want to work out is the probability that x is less or equal to 50. Now in terms of working out the lower bounds for both the on your calculators, because obviously when you're doing values you need a lower bound or upper bound. Now generally speaking, your upper and lower bound, you really want to pick an extreme value. However, more mathematically they tend to go for that the mean plus or minus 5 lots of the standard deviation. So if you see in some textbooks or some exam papers that to work out the extreme lower or upper bound, then this is the kind of formula that they do use. But if you were to go for a really crazy big number or really crazy small number for your values, for your upper or lower bounds, then that would be absolutely fine. It should give you the exact same answer. So for this, if I type in for binomial and I work this question out, I should have the answer of 0.999 I get. And then if I then do a normal distribution with the parameters of 27 and 14.85, then, and I want to work out the probability that x is less than 50, then again, what I need to, 50.5 I should say. So I'm going to enter those values in and I should end up with an answer of 0.99 as well. And again, you can see that those two answers there are practically the same. So moving on to our part C. And let's go to green. So for C, again, we're looking for values that are greater or equal to 12. So the probability that I want is where x is greater than 11.5. So that's going to be my continuity x correction. Then for 2, in terms of binomial, so again, using the parameters of 60 and 0.45, working out the probability that x is greater or equal to 12, which is 1 minus the probability that x is less or equal to 11, and that should give me an answer of 0.999970, and then for, or 86 I should say, I'm looking at value 86. And then for a normal distribution with the parameters of 27 and 14.85, and again let's square root that and there. And what I'm looking for is I'm looking for this, so it's going to be the probability 1 minus the probability that x is less than 11.5. Again, or you can work it out in terms of your parameters. It shouldn't really make a difference. Should end up with the same answer, and which we get 0. And that should be a y, not an x. And then what we then get in as an answer is 0.999970. And again, in terms of comparing those two values, or those approximations, you can see that those two numbers there are very, very similar. So then moving on to D. So this is where we've got an actual set of limits, which in theory should be a little bit easier, to be honest. So with D, our continuity expression correction is going to be, well, we're wanting to include 32 and 51. So then I'm going to need to go for the probability that x is the lower bound of 32, which is 31.5, and the upper bound of 51, which is 51.5 rather. So that there's my continuity expression, and then working out with the binomial, we've got 60 and 0.45, and then so working this out on the binomial, so probability 32 x and 51, so I can do that straight onto the calculator, and I should get an answer of 0.121465. And then working out with the normal distribution with 27 and root 14.85 squared. Again, I'm working out the probability that 31.5 y and 51.5. So your lower limit is going to be 31.5. Your upper limit is going to be 51.5. Mean is 27. Your standard deviation is root 14.85, and that should give you an answer of 0.12145. And again, you can see that those numbers there are very, very similar. Again, moving on to E. And let's not go for yellow, let's go for red. So for E, our continuity expression. Now here we wanted numbers that are bigger than 17. So again, looking at continuity expression, I want x is greater than the upper limit, which is 17.5. Then looking at the binomial expression, so again setting the parameters of 60 and 0.45. And again, what I'm working out is x is greater than 17, which is 1 minus the probability that x is less or equal to 17. Don't know what kind of 7 that is. But again, entering that on your calculator should give you a value of 0.99391. And then working with a normal distribution of 27 and root 14.85 squared. And we're working out what the continuity expression is. So x is greater than 17.5, which is 1 minus the probability that x is less than 17.5. And working that out, that should give us a value of 0. And it's going to be 99315. Again, as you can see, these two numbers here are very, very similar. Then finally, moving on to F. Now with F, and let's go for this little pea green. So with F, we're looking for values that are less than 40. So my continuity expression, because I don't want to include 40, is going to be where x is less than the lower bound, which is 39.5. And then for part 2, working out the binomial. So again, setting up the parameters. And what I wanted to work out is the probability that x is less than 40. So that's going to be the probability that x is less or equal to 39, because obviously we're looking at discrete data. And then from this, what we should have is that this equals, and again using a calculator, 0.99941. And then with a normal distribution, again setting the parameters, I feel like saying these numbers all day. And I want the probability that x is less than 40. And again, I just simply bung that into the calculator, and that should give me a value of 0.99940. And as again, as you can see, those two numbers there are very, very similar. And now one thing I've just spotted in terms of the notes, that this should be sigma squared, because obviously the variance is sigma squared and the standard deviation is sigma. But again, all the other calculations are correct. So let's have a look at example 2. Now example 2 is, I would say, very, very similar to what you could expect in an exam question. So it says a random variable x is normally distributed with a mean of 26 and a standard deviation of 6. An independent random sample of size 6 is taken from the population. Find the probability that more than 3 of the observations are greater than 24. So let's have a look at the key bits of information. So in terms of the solution, let's first set up the parameter. X is assumed to be normally distributed with a mean of 26 and a standard deviation of 6, so I can write 6 squared. Now for this, what we need to do is, now obviously this gives us the information for a normal distribution question. However, this part here is the binomial part. And so what we need to do to find the binomial, so if the final part of the question is binomial, we need to know what the parameters are for the binomial. So with the binomial, I need to know sample size, which I know is 6, but what I don't know is the probability of getting a score more than 3. And so in terms of greater than 24, so what the probability of x being more than 24. So first things first, well, what I need to do is I then need to use normal distribution to find this. So use normal distribution to find P. And that is the very first thing that I then need to do. So what I then need to do is, with this parameter, I need to work out P is greater than 24. Now I can use my calculator for this. So I'm going to use NCD on the calculator. My lower bound is 24. So if you imagine that, here's my normal distribution graph, drawn very, very poorly. and this is a probability that I'm wanting. So the lower is going to be 24. The upper, again, you can pick absolutely any value, but what they tend to prefer you to do, or in some textbooks, is go 5 lots of the standard deviation. So again, it's the mean plus or minus 5 lots of the SD. Again, but you can pick an extreme value and it should give you the same. Sigma is 6 and mu is 26. Now, if I type that into my calculator, which I'm going to do right now, so just bear with me. So I've got 24, I've got 24 plus 5 lots of 6. Sigma is 6, which gives me 54. Mu is thingy, and I get an answer of that P equals 0.630557, and that continues. So this is my probability that I then need to use. So in my binomial distribution, I know that this answer here is going to be 0.63 and with a few decimal places. So then, setting up the binomial parameters, I've got 6 and I've got 0.6305 and then whatever you want to round that up to. And what I'm wanting to work out is the probability that x is greater or more than 3. So from this, what we then need to then do, now again, let me just notify this is the probability of getting more than 24. So working this out, that's going to be equal to 1 minus x is equal to or less or equal to 3. And again, if I type that all into my calculator, so let's just do that now. So I've got x is 3, enter those values in, and I get 1 minus 0.3924, and then carries on. And then working it out, I get 0. And then it's going to be 608 to 3 significant figures. And there is my final answer. Now looking at question 3, you can see here that this question is very, very similar. So it says the mass shown on packets of red lentils is 1 kilogram. To satisfy weights and measures legislations, the manufacturer ensures that the mean weight of the bags is 1.003 kilograms with a standard deviation of 0.004 kilograms. Find the probability that out of 8 bags checked, less than a quarter of them are under 1 kilogram. So for this, again, this first opening statements mentioning the means and standard deviations represents the normal situation, and then this latter part is binomial. So working with the solution of this, so what I need to do first is using normal distribution is find the probability that x is under 1. So in terms of this, we set up our parameters that x is assumed to be normally distributed with a mean of 1.003 and a standard deviation of 0.004. So typing this in, this is what we want to find. So probability that x is less than 1. So I keep putting less or equal to, it's just instinct. And again, I'm going to go for NCD. My lower is going to be an extreme value. So for this, I'm going to go for 1.003, and it's going to be minus 5 lots of the standard deviation. And again, if you type this onto your calculator, it should actually work out for you. So you can actually type it in. You don't need another calculator to do that. My upper bound is 1. My sigma is 0.004. And my mu is 1.003. If I just quickly do that on my calculator and do just that, so I've got the lower is being 1.003 minus 5 lots of 0.004, and it gives us this 0.983. Then the upper value is 1, and sigma is 0.004, and mu is 1.003. In which I get a probability answer of 0.2266, and that continues. Now again, if I just quickly do that as a graph and just show as a picture, I've got 1, and I've got, so that's 1.003, and what I'm wanting is to work out what this probability here is at 1. So now that I've got my P, I can then work with my binomial approximation. So here we've got binomial, we're thinking with a sample out of 8, and my probability of success is 0.2266. I'll write it to 4dp, and what I'm wanting is the probability that let's say just say y is less than a quarter, so y is less than 2. So that's what I'm wanting to work out. So then working this out on my binomial distribution, so this then is going to be equal to the probability that x is less or equal to 1. So again, what I'm going to go for is BCD, and here on the calculator, let's quickly access that variable. So in terms of variables, x is equal to 1, n is equal to 8, p is equal to 0.2266. So if I type those values in, so I've got 1, 8, and then I've got 0.2266, I get an answer of 0.428 to 3 sig big. And there we go. And you will tend to find that a lot of exam style questions, either part C's of a binomial distribution question or a normal distribution questions, looks like this. So whenever something's being mentioned in terms of sample size, or a sample's been taken out after, or you've talked about mean and standard deviations, then the question is going to involve a normal approximation with binomial distribution.